Hello, I'm Ethan Armis, and this is the Physics 2 Lab 4. This lab was constructed for the purpose of observing magnetic properties as it pertains to the Biot-Savart law and a bar magnet. Below you can see the equations that pertain to the Biot-Savart law and how it defines a magnetic field. In this experiment, we had a bar magnet at the end of a meter stick with a magnetometer phone app on it, which we would move along the meter stick. The system is the bar magnet itself, and the surroundings is the phone and the environment and the meter stick and all of that. At the end of the experiment, after observing the magnetic field multiple times at many different distances, we calculated the magnetic moment to be 161,481.921 Tesla area squared. This is very big, and as the computational model does not reflect the experiment because of this. We'll talk about sources of error towards the end. But some assumptions were made in this experiment, which is that we're operating in a vacuum and that there are no other net fields. Here you can see the Excel spreadsheet where we recorded the magnetic field value that we recorded at various different locations. We found the average of it, and then we also found some magnetic field locations perpendicular to the meter stick. From our linear regression of the plot, we're able to calculate what the magnetic moment is. As you can see, the value for n is our slope, and k comes from, there's the natural log of b, which is the magnetic field, and that pertains to the y-intercept. So if we were to take our y-intercept and raise it from an e, then we would solve for our k value. And using those, we can rewrite the Biot-Savart law and calculate our magnetic moment. This is the computational model that I made for the experiment. It models the experiment that we did, but of course in a more mathematical and perfect environment. And here is here's the photo of the model itself, where you can see the vector arrows for the magnetic field itself. And of course, this is characteristic of a magnetic dipole, which the bar magnet is. You can see right here the values that were calculated for the magnetic field at different points. There's the two that are on the axis, which were both about a magnitude of 32.29 Teslas, and then those around perpendicular, which were negative 16.14 Teslas. Moving on to our discussion, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The component vectors of our measured magnetic field from the phone magnetometer would each include some inaccuracy from the component vectors of Earth's magnetic field, which would be difficult to mathematically account for. And then secondly, what if you were to stick two identical magnets together end to end and run the experiment again? How do you expect your measurements to differ? If their poles are aligned, then the magnitude of our measurements would have doubled, but in the same directions, as the fields of the two magnets would compound. So in conclusion, this lab demonstrated in a physical way how magnetic fields look and what their vectors are at different locations. The values that we got from calculating the actual experiment and from the computational model, of course, differ quite a lot. And the sources of error between the experiment and the computational model can be attributed to slight magnetic fields interfering from other sources, an inaccurate magnetometer phone app, and of course, an imprecise alignment of the meter stick to magnetic north. Thank you.